Okay. Check that's actually working. Hello, hello, hello. All right, welcome to my lesson. My name is Mr. Johnson. This is chemistry, and the lesson is on the groups of the periodic table. There was a technical hitch with the previous lesson I did, so I'm just going to try and share my screen with you now, and then I'll pop out and just check with you all if you raise your hands and let me know once I've shared the screen if you can see. So, okay, so at the moment I've got screen sharing, and we do have a member of staff just in the background. If you would possibly just let me know if you can see it. Okay, brilliant. It looks like it's all fixed. Thank you everyone for your patience. As I said, my name is Mr. Johnson, and this is a GCSE lesson for chemistry, periodic table, and groups in the periodic table. So, prior knowledge. Some of the prior knowledge that you needed for this is describe how Mendeleev arranged the elements in the known at the time into the periodic table using prior ideas. Describe how Mendeleev predicted the position and properties of the unknown elements and the problems in his approach, and explain the discovery by Moseley around the atomic number that helped confirm Mendeleev's ideas. These ideas are crucial to what happens in this lesson, where here we're going to describe and explain the main properties of the noble gases, including their reactivity. Then we'll move on to a different group and we'll describe and explain the main properties of the alkali metals, again including their reactivity. Finally, we'll describe and explain the main properties of the halogens, again including the reactivity. So, periodic table is common in science classrooms worldwide. The names and symbols of the elements are internationally recognised. Whatever country you go in, whatever country you view it in, they will all be the same. This allows science to be a universal language. All of the elements in this table have been arranged in groups based on similar chemical and gradually different physical properties. We're going to look at 3 groups in particular. The modern periodic table, just as a recap, is not arranged by mass, but by the atomic or proton number. Elements in a column or group show similar chemical properties to others in the group. Elements in a row or period increase in atomic number from left to right. So you can see from lithium to beryllium to boron, carbon, nitrogen, the atomic number is going 3, 4, 5, 6, 7, and so on. Metals are on the left of the table, with the non-metals on the right. Now we're going to look at the last column or group of the periodic table, the noble gases. Noble gases are what we call group 0 of the periodic table, this one here. They are monoatomic elements. The atoms do not bond with another atom of the same element. In fact, they're inert compared with the other elements. They don't react with anything. It's very difficult to make them react with anything else, including each other. They contain, from top to bottom, the elements helium, neon, argon, krypton, xenon, radon, and organosine. Properties of noble gases then. All the elements in group 0 are relatively inert. As a chemical property, they really are very difficult to make react. They have low densities, which is a physical property, and they're non-flammable. Because they're unreactive, they won't even react with oxygen, they won't ignite, there's no flame. These are general properties that we can take advantage of then when using the noble gases. So, some example uses. Xenon and argon are used in filament light bulbs instead of air around the filament, and this stops the metal filament reacting with oxygen when it's getting hot and burning away. It extended the life of the bulb. Argon and helium are used in welding when you're fixing 2 pieces of metal together, and this forms a blanket over the hot metal which displaces oxygen. It moves it out of the way. That stops it reacting with oxygen from the air. Helium Well, you've all heard of helium, you get it in party balloons. It's very low density, it's lighter than air, and so it's used for filling weather balloons and airships. Argon. Another use of argon is in fire extinguishing systems because it's non-flammable. Places like computer server rooms where you couldn't use water in the event of a fire because it's an electrical room filled with electrical equipment, you can use argon instead. And what that does is it pushes the oxygen out of the way, which cuts out the oxygen supply for the fire, which puts the fire out safely without introducing an electrical fire. Finally, neon. Neon's often used in fluorescent lamps. You've probably heard of neon sign and advertising displays because it produces a red coloured light when electrical current is passed through it at low pressure. Explaining the reactivity then. To explain the reactivity, we need to consider the electron shells. All the elements in group 0 have a full outer electron shell. Helium, it's in the first period or row, so it has a maximum of 2 electrons in its outer shell and it has both present. Neon, in the second period or row, has a maximum of 8 electrons in its outer shell and it's filled. The same with argon. And we use the notation 2 for helium, 2,8 for neon's electron structure, 2,8,8 for argon's. Elements in other groups gain full electron shells by forming ions, losing or gaining electrons, or by forming covalent bonds where they share electrons with other groups. These guys don't have to do that because they already have a full shell. Because they have a full shell, it makes it very difficult to make them react at all, because they don't need to gain or lose electrons in any method at all. So let's describe and explain the main properties of the noble gases, including reactivity. Second outcome, describe and explain the main properties of the alkali metals, including the reactivity. So back to our periodic table again. The alkali metals are in group 1 of the periodic table. They share similar chemical and physical properties to each other, and that's why they're in the same group. This is group 1. As you can see, we've got 6 members of group 1. They're all held together by metallic bonding because they are metals. They all react with water to produce an alkaline metal hydroxide and hydrogen gas. And the general equation for this is alkali metal plus water. When you combine them, react them, make the products metal salt and hydrogen. Now the key thing here is the reactivity increases as you go down the group. Lithium reacts the least violently, francium reacts the most violently. They contain from the top to the bottom, the elements lithium, sodium, potassium, rubidium, cesium, and francium. So some of the physical properties of the alkali metals. All the elements in group 1 are solids at room temperature. They have low melting and boiling points compared to other metals. Sodium actually melts at about 97 degrees C, where something like iron's above 2000. They're soft metals that can be cut with a knife. I myself have done this demonstration hundreds of times in the classroom now, and I've used a butter knife before now to cut a piece of the alkali metal off in front of kids in the classroom. They have low densities. Lithium, sodium, potassium actually float on water because they're less dense than water itself. These are the general properties we use to characterize the alkali metals. So the reactions of the alkali metals. We've already mentioned alkali metals react with water, but one of the most common questions, especially 6 marks, is to describe the reactions of 3 metals, lithium, sodium, and potassium, and to use this to prove the order of reactivity increases as you go down the group. So let's take a look. Lithium. If you were to put lithium into water, you would have seen this yourself if your teacher's done it in front of you in class. The observations that you make are that it floats on the water. It does fizz, effervescence is given off, and this is because of the hydrogen, and it moves around the surface because of the bubbles being produced. Not very quickly though. It gradually disappears as the reaction completes. It dissolves into the water as it forms a metal salt. The hydrogen being produced, the effervescence that's given off, does not get hot enough to ignite in this reaction all by itself. So you never see a flame with this reaction. Next metal, sodium. Observations of sodium when added to water is that, again, it floats on the water, but now it fizzes more and moves around the surface faster than lithium. This next bit is a bit odd, but if you've seen it, you'll know what I mean. It forms a molten ball. It almost seems that the ball is kind of, the only way I can describe it is if you've ever seen a chocolate fountain and you've seen the chocolate fountain down, the ball seems to do that as it's sat on top of the water. And as time goes by and the reaction carries on, this molten ball gradually disappears as the reaction completes. Sometimes the hydrogen that's produced by this reaction, the effervescence that's given off, does catch fire due to the heat produced by the reaction, usually when the sodium is getting trapped on something like the wall of the container. If it does, then it will ignite and it will burn with a yellow flame. Our final metal, potassium. Observations, and again, a lot of these are common. It floats on water, but this one fizzes most. It still fizzes just like the other two, and it moves around the surface faster than the other two, that also move around the surface. Again, like sodium, it falls a molten ball, but this time it very quickly disappears as the reaction completes. And finally, the hydrogen produced always catches fire due to the heat produced by the reaction. And I apologise for the spelling mistake there, but it burns with a lilac flame, which is characteristic of potassium. The gradual increase then in violence as you move down the elements of the group established that the chemical reactivity increases as you move from lithium to sodium to potassium, i.e. as you go down from the top to the bottom of the group. And this actually allows you to predict the properties of the next element in group 1. For example, if you were talking about rubidium, you might say that it might explode in the water. It will produce hydrogen gas very, very quickly. It will get very hot. It will definitely burn. Because you know that potassium is the baseline and it should do what potassium does more violently. Explaining the reactivity of these elements then. All the elements in group 1 have one electron in their outer shell. The electron structures on the right hand side. You can see the lithium, 1 in its last shell, sodium, 3 shells, period 3 element, 1 electron in its outer shell, potassium, 4 shells, 1 in its outer shell, because period 4 element. They gain a full outer shell by losing that outer electron and forming a positive ion. Now the thing is, if they all do this the same way, why then is it more violent for potassium? Why does potassium react faster than lithium? And it's all to do with the size of the atom. So let's take a look. As you move from lithium to sodium to potassium, the atomic radius, i.e. the distance between the outer shell electron and the nucleus, is getting bigger. So that means the outer shell electron is further away from the nucleus as you go down the group because the atom's getting bigger. This then means that the attraction between the electron and nucleus that holds that electron in place is weaker because 1, the distance is bigger, and 2, the more shells you've got, the more there are in the front of it getting in the way. This then means that it's easier for the atom to give up its outer shell electron to another atom that wants to take it at the bottom end of the table because they're bigger and they're not holding on to it as much. So that makes the bottom of group 1 more reactive. That's our second outcome, describe and explain the main properties of the alkali metals, including reactivity. Final one, describe and explain the main properties of the halogens, including reactivity. So the halogens then. The halogens are in group 7 of the periodic table. This is all the way over nearby the noble gases, and it's this group here. They're all simple molecular elements and they're made up of molecules containing 2 atoms. For example, chlorine exists as Cl2, fluorine exists as F2, 2 atoms of each bound together. They are non-metals and they react with metals to form compounds called metal halides. The general equation for this is a metal plus halogen will form a metal halide. The reactivity increases as you go up the group. This is different to our group 1. In fact, it's almost like if you pinned a piece of wood to the middle of the periodic table and pushed the group 1 side down, to say the reactivity is going that way, the group 7 one would go up. It's a bit like a seesaw. As that one goes down, reactivity increases, group 7 goes up, the reactivity increases. So fluorine is the most reactive halogen. They contain, from top to bottom, the elements fluorine, chlorine, bromine, iodine, and astacine, and at the very bottom there, tennessine. Physical properties of the halogens then. All the elements in group 7 are held together by covalent bonding. They are gases, fluorine and chlorine, liquids, bromine, and solids, iodine and astatine at room temperature. So this means that their state gradually changes as you go down the group. This is a change in physical property, which is gradually changing as you're going down the group. They have low melting and boiling points that gradually increase as you go down the group, which is why the top of the group, fluorine and chlorine, are gases, liquids, bromine, solids, iodine, because as you go down, it takes more than room temperature to heat them up to the point where they'll turn to a gas. They also have low densities, and the densities do increase as you go down the group. These are the general properties we use to characterize the halogens. Now, we use the displacement reactions of the halogens to help establish or prove the order reactivity of the halogens. All the elements in group 7 then can react with hydrogen to form a hydrogen halide. For example, hydrogen and chlorine will form hydrogen chloride, hydrogen and fluorine, hydrogen fluoride, hydrogen and bromine, hydrogen bromide. And if you dissolve these in water, then you'll get a solution which is acidic, so hydrochloric acid, hydrofluoric acid, hydrobromic acid. We can use displacement reactions of these hydrogen halides to prove the reactivity of the halogens. So let's take a look at a classic reaction that you might have had to do in school using dimple trays. Displacement reactions can be used to work out how reactive the different halogens are. A more reactive halogen will displace a less reactive halogen from its compounds. We can use the hydrogen halide solutions of chlorine, bromine, and iodine in the school lab to prove it. So displacement reactions. I've got a solution containing KCl, which is potassium chloride, KBr, which is potassium bromide, and Ki, which is potassium iodide. These are metal halide solutions. If I react them all with chlorine solution, KCl gets no reaction because the chlorine won't displace itself. KBr, with chlorine added to it, will change colour. A reaction is seen because the chlorine is more reactive than the bromine. Ki, when you add chlorine to it, changes colour. Again, a reaction is seen. So this gives chlorine a score of 2 reactions out of a possible 3 because it can't react with itself. Bromine, when you add it to KCl, has no reaction. Now this means that chlorine, which is present in KCl, must be more reactive than bromine, and so it will not allow it to displace it. KBr, potassium bromide, added to bromine, you get no reaction because it won't displace itself. But when you add bromine to Ki solution, potassium iodide, you do get a colour change, which means that the bromine has displaced the iodine, making it more reactive. This gives bromine a score of 1 reaction. Finally, iodine, and unfortunately for iodine, it's at the bottom of the pile. If you add iodine to KCl, there's no reaction, and KBr, there's no reaction, meaning that both Cl and Br, chlorine and bromine, must be more reactive than iodine, and so they will not allow displacement. Iodine added to potassium iodide, you get no reaction simply because it will not react with itself. So that gives it an overall score of 0. The higher the ability to displace the other members of the group, i.e. the bigger the score, established that the chemical reactivity increases as you move up group 7. Remember, chlorine was at the top of group 7 out of these 3 elements, with bromine in the middle and iodine at the bottom of the 3. Explaining the reactivity then. Now this is very similar to what we saw with the alkali metals. We're still talking about the electron shells. The elements in group 7 have 7 electrons in their outer shell. They gain a full outer shell now, not by losing, but by gaining 1 electron and forming a negative ion, and they gain that 1 electron from another atom nearby. If they all do this the same way, why does the reaction become less violent as you move down the group? And again, the answer is to do with the atomic radius, the size of the atom. As you move down from chlorine to bromine to iodine, the atomic radius gets larger. This means that the outer shell electron of the atom it's trying to steal the electron from is further away from the nucleus of the halide, of the halogen. This then means that the force of attraction between the electron in that electron shell and the nucleus is weaker because the distance between the two is greater, and there's more shells in between. That then means it's harder, as the atom gets bigger, for the atom to take another electron into its outer shell from another atom, which means it's less reactive, it's less effective at stealing. And that's our third outcome: describe and explain the main properties of the halogens, including the reactivity. Okay, so I just want to say thank you very much for listening, and I apologise for the problems at the start. Take care and speak to you again soon. Sorry now.